Okay, welcome back. We are going to very quickly revise the code that we worked on yesterday. The CIT fixed the R here, but I think to play it safe, I actually made a document with all the results. So I won't be running R formally, but you can run R your machine to see whether you get exactly what you have. So I won't dwell on this too much. You learn how to read in a CSV. Well, first you learn how to put this. First you learn how to make a directory, a file folder on your desktop, and name it. You learn how to point R to it by using setwd. Then you also save a CSV file that I put on Moodle and you put it in the folder. And then you read from it. So there's already 4 or 5 things. Once you've read it, you can see what it looks like by running, just calling for the name, running that line. So you get the whole data set. That's what I've done. Remember, head gives you the first 6. What gives you the last 6?
Tail.
Very good, right? So, and then what else? We also learned how str, this command actually tells you the structure of the thing that catalyst M is. It's a data frame. To explain what that is, it's a spreadsheet. The data frame can be thought of as a spreadsheet. And then it also tells you how many variables you have and the values that it takes, right? And in this case, the response was concentration. Okay. Then I gave you code for plotting a box plot. And that was easy enough. You could have seen something like this. And then we introduced ggplot2. I ran through quite briefly how this works. You can tweak this to talk about what colors you want, how many bins in the histogram you want, how bright the color is by using the alpha parameter like that. All right, so you have this. Then this is important. We also talked about tapply. And again, remember the order. The first thing in tapply, the first argument is always the which variable? Explanatory or response? Response first. Response, then the explanatory, which is the catalyst type here. And what was the deal with the S dot factor thing? Does anyone remember? Why is that important? Why is S factor important? Or when is it important actually? Anyone remember? Yes.
You have to say that the variables are categorical.
That's right. You use S factor when the variable, and dollar sign means variable. Variable called this. So when your variable is categorical, it is good practice to put S factor. I say this because officially, for catalyst, you don't have to, because catalyst was coded in. But if catalyst had been called 1, 2, 3, 4, you're in trouble. So good practice, categorical variable, put in S factor. So the response, explanatory. Then what statistic do you want? Right? Do you want the median of the group by group? Median by group? Do you want the sample size by group? Do you want the means by group as these? Okay, so this is a very useful and very important command that we'll be using a lot. Tapply. No pictures, right? We then introduced the Brown-Forsyth test. Anyone remember what it's for? I don't even give you the, yes.
It's for comparing the population standard deviation.
Yes. And to use a big word, the homogeneity of the spread. The homogeneity of spread. Is there evidence of non-homogeneity? And so the alternative hypothesis is that there is non-homogeneity. They are not homogeneous. So with a p-value this large, we do not reject the null state. So the null says that the variances are homogeneous. It can be confusing sometimes because there are so many statistical tests. Sometimes it's not clear what the null is saying. So that's why this is very helpful. They actually tell you the alternative is that they are not identical, which means the null is that they are. And so with this kind of p-value, we do not reject null. So in other words, inference proceeds per norm. And then we went to S-pooled. Remember how S-pooled is defined for when you have just 2 groups? When you just have 2 groups, you just have this term and this term, and you can shut off the rest. You have total sample size less the number of groups that you have. So in this case, it's 4. Please be careful. And that's why you have this plus this. And today we will be working on an exercise, pretty long, but you'll get your feet wet and do all these things. So we'll do that after I've done reviewing this thing. Then how do you find the square root of anything in R? Just SQRT, like that. Remember that in R, if you want a variable to be named, give it a name. If not, it's just going to calculate stuff and tell you the answer. I didn't name this, I just asked for it. So, and don't worry about this. This just indicates that this is actually just one element in a vector. So it's a technicality. So just leave it over. Okay, we learned about the grand mean, labeled y bar dot dot. What is the grand mean? Well, it's the mean everyone understands. Take everything and regardless of groups, find the mean. That's why it's called the grand mean. The grand mean is useful because in the definition of the Snedeker F statistic, it uses it. So I think this is actually quite telling. Let's look at how do you calculate Snedeker's F? First of all, there's the numerator. Remember, the numerator involves within or between group variability from yesterday. Do you remember? I gave you a qualitative way of looking at it. I'm not going to ask you for the formula. But what was on top in F? It's a ratio of two variabilities. What's on top? Between, good. And what's at the bottom is within. So what we are finding here is the between group. Why is this a between group variability measure? Because notice you're taking 56.9, which is the mean of group A. You're taking 55.775, which is the mean from group B, if you check the key applied. So what are we doing? We're taking the group means, subtracting the grand mean each time, and finding the disparity. That's why this is a between group variability measure. And you divide by the within group variability measure, which is what actually it was revealed yesterday that the within group variability is the yes, good. It's just that technically the F statistic divides by S pooled square. But it's basically it is S pooled square. And does it make sense to you that S pooled is a within group variability measure? It does, doesn't it? Because look at how it's found. How is S pooled found? S pooled is found. It's just here. S pooled is found by taking the standard deviations of each group separately. See, this measures the variability within group 1. This measures the variability within group 2. So you are adding up the variabilities within the groups. That's why the formula is found. And the good part is, even if you don't understand what I'm saying, you can actually get full points if you know how to tweak stuff. But I'm trying to give you more from this stats class, telling you why things are to be done. Not just throwing a bunch of formulas at you saying, putting this. What's the point? Right. Everyone can use a calculator. I'm trying to give you the logic. So when your between group variability is higher than your within, then does it indicate possibly that there is a difference? Right. The groups are more different between themselves than within themselves. And that's why a large F statistic leads you to reject or not reject the null. Reject. A large F statistic will yield a small p-value. Why? Because the F curve, again, looks like a chi-square curve. You push to the end, your area is rare. That kind of F statistic is special. It's rare if your null is true. Not impossible, but rare. The same rationale for what? We can never prove whether the null is true. It's all an evidence game. I'm not saying I've proven the null is true. We never can. But if the null were true, your F should be small. A large F can happen, rarely, if the null is true. That's the whole logic. It's the same logic actually from day one of this course. It's just that it's not being applied to data structures that are more complicated. All right. Okay, so we have this. We calculated this one. And we found that the F statistic is 9.915. Okay, so to do a very quick review, I taught you how to read the F table, right? So we will revise that. The F table already exists on our page. All right. You will remember from yesterday that the F table has how many degrees of freedom to look at? How many degrees of freedom are there in an F? 2. We call them the numerator and denominator DF. What was the numerator in this catalyst example? The numerator DF. Sorry. How many catalysts are you comparing? How many catalysts were there? A, 4, A, B, C, D. Which means what's the numerator here? 3, less 1. Good. How many data points did we have? 16. And what's the rule for the denominator here? Total sample size less number of groups, right? Which was 4. So there's a lot of do I minus 1, do I not minus? That's what cheat sheets are for. So 16 minus 4 is 12. So look for 3, 12. So 3 is the numerator here, so go to column. And it turns out that this page has 12 on it. So it's a happy coincidence that everything is in this page. If not, you have to go to another page. So 312 would be, and how do you read this? Okay, did we say the F was 9? 9 is between 5 and 10. Means of two values between 10. Okay. Then we ended on something yesterday, which I want to go through. We ended on a new command that I wanted you to try, which is called the AOV. And you can go and do this on your own time. I will show you the output today. What is AOV? So first of all, AOV is an acronym to stand for the analysis of variance. And it's basically an analysis of the variability in your data. It's a receipt. I always tell students, some people call this ANOVA, analysis of variance. So when you run this again, look, response, tilde, explanatory, where does the data come from? Same formatting. Writing this, though, gives you what's called the ANOVA table. ANOVA table is something that by the end of this semester, you're going to be kind of sick of looking at. And they are going to get a bit more complicated than this as the models. So it's very important from the start. You know what an ANOVA table even is. All right. First of all, an ANOVA table is a receipt. Now, when you go to a supermarket, that's the best example. When you go grocery shopping in a supermarket, don't they itemize your bill for you? Some don't. I think I was in Walmart just a few days ago, and I bought quite a few things. They did not itemize. So you kind of have to figure out, and it's kind of cryptic, sometimes. Like, what did I buy for $3.15? You can't tell because it's not very descriptive. But I have been to supermarkets where they actually itemize. Like, this was a dairy. This is exactly dairy, clothes, apparel, whatever. Yes, this is a receipt. It means, and what is sum square? The sums of squares are like dollar amounts, but they are dollar amounts of variability. The higher your sum of square, the higher the variability in the whole system. Now, this is a very simple model. So this receipt has only 2 things. All right. So you can think of this as $85 and $34. What's residual? Now, the word residual in English means what's left behind. In other words, the residual variability is what the model cannot explain. Some people, and I might as well tell you now, some people call this error, which I don't like because it has a connotation of being wrong. It's not wrong, but that term has stuck. So you may see textbooks which use the term error. So just be careful. I don't like it. I prefer residual or resist. It's what's lacking. It's what the model is the shortfall. So I always give this illustration. I'm not that kind of person, but some people are. When you're young, your mom gives you money, you go to the store. She asks you to buy 10 things, and you buy like 12, and 2, you don't want to tell what you bought. So it's kind of like these are the things your mom asks you to get. And these are the things you don't want to explain to your mom what did you get. It's unexplained. The model can't explain. In other words, let me ask you now intuitively, will a good model or a model that can tell you a lot, should it have a small residual or large residual?
Small residual.
Right. So you can already tell, just based on dollar amounts, do you think this model is pretty okay? It's not bad, you know. It's not that bad. All right. So that's key number 1. And an ANOVA table is a receipt. It's a variability receipt. And the variability is actually measured in the sums of squares like that. Okay. Do you see a 3 and a 12 here, the DF? That's the numerator and the denominator DF. Right? These things will become more and more important as the models get more and more complicated. Right now it's easy. See, there's 12, that is the unexplained part. Does it make sense? Okay, therefore, I want to show you, do you see that the F value is given here automatically, that we calculated by hand? Look, right? And even more interesting, you will actually find that if you take the square root of the mean square residual, this number is your S pool. Why does that not surprise you? Because the F statistic is the ratio. Okay, so let me show you in a bit more detail how the ANOVA table works. To explain the degree of freedom, we have talked about that. These are variabilities. I'm here to tell you these numbers are not mysterious. They are actually found by doing the thing which I asked you to calculate when you made the F statistic. See, the F statistic is a ratio of 2 things. It is actually the ratio of 2 mean squares. So what is a mean square? A mean square is simple. It is just a sum of squares divided by the DF. So if you take 85 and divide it by 3, you get 28. Like that. If you remember yesterday's formula, which I wrote on the board, the F statistic was a whole bunch of things divided by k minus 1, if you remember. That means the numerator and denominator of the F statistic are 2 mean squares that you find the ratio of. Does it therefore tell you that you can get your S pool from here? S pool is the square root of this because this number is the denominator of the F statistic. This number is the numerator of the F statistic. The 28 is the numerator of the F statistic. The 2.8 is the denominator of the F statistic. And we know now that the denominator of the F statistic is S pool squared. So to get S pool, you take the square root of 2.8801. And that is why one way to remember what is S pooled, some software, this one doesn't. Some software know how important that is. They declare something called the RMS, the root mean square error. You may have seen this in some statistics output if you use some other software. The RMSE, the root mean square error, what is that? I told you some people call this error the root mean square error. If you take the square root of this number, you get S pools. And I will let you demonstrate these things in a group exercise. Right? So what I'm saying now will be more illuminated by what you can do. And I'll give you part by part what to do. Okay, this part is something which the software gives you. It's not so important because I've actually taught you a more comprehensive way to see this. They're trying to give you the means of the groups. So you don't have to use this command if you don't want to. This doesn't seem to give you the SVs, you see. It may work for SVs, I didn't try, but you can use T-apply. I don't recommend using this one. This was given by the textbook. I think T-apply is easier to use. All right. Okay, so that explains this. Last thing. Here's the p-value, which the table tells us is between 0.001 and 0.01, which is true. This gives you the exact P value in the F statistic. All right. Okay. So I did say notice the MS resid value. It is S code squared. Okay, that is the end for the review for now. So what I'll do is I will give you an assignment to work on with your group, as usual. Not Moodle, it's one of those Google Drive things. I want you to do it from scratch where you make the CSV file and all that. So please ask me if you don't know or remember how to do something, especially R related, like how do I read in a file and all that. I will help you, right? So here's the exercise that I want us to work on. It's group work 24. It's a very long one. So we will see what we can do today and see how far we go. I will give you the whole thing, but some things I've not covered yet. We will complete it after I've taught you other stuff. So let me paste this onto our class record as usual. And we look at it together. Okay, so this is group work 24. So to help you get some exercise or get some experience making a CSV, I did not make a CSV of data. I want you to go to the Atkins versus other diets tab in our datasets Google Sheet. If you go to the datasets section, the Google Sheet is removed there. It's called data. The dataset is called the Google Sheet is called datasets. Click on that one. Go look for the Atkins versus other diets tab. Select the cells there. Make your CSV file the way I told you. Does anyone remember how to make a CSV file? You just go to File and download as. Okay, okay. So go do that. Put it in your directory, and I think you know what I'm trying to do. So make the CSV file. Then start answering the question. Use the code that I gave you. Okay. So I'm going to stop talking now. Any help you need, just raise it.
Yes.
You want it to? Yeah, sure. I'm actually quite excited to look at the histograms using the code that I gave you, but I haven't even plotted them myself. So as you work on this, as usual, try pasting your histograms and pictures here. Just do a screen grab and just. Let's see if we can complete up to question 8. Right? You can't do 9. Well, you can, but I want to leave 9 for next week. So let's try to do everything till 8. And then we're done for today. Let's see if we can finish up to 8. And I know I've not talked about the validity conditions. I want to see if you can come up with what they should sound like on your own. So give it a try. All right. Oh.
I tried it with it's like the title of it called diet. So I tried it with diet and I like to try.
Yeah, I think data set is okay, right?
Yeah, it read it.
In fact, is the histogram working?
I look at this.
Oh, okay. Can I see your Atkins ranking? Run down, down. Because diet,
It should be
yeah,
diet.
it's always response to the, so, yes, so it's always response to the explanation. So, and case is important. You know, because so so you can't say BMI to the Atkins because, um, oh, sorry, that is, yes, it's not Atkins, it's BMI to the diet, to the hypertrophy, because that's the variable. Atkins is just one of the levels. That should work, doesn't it?
Wait, no.
No. Now it's saying, yes. Try to keep it. Did you run library?
I haven't closed it since I read that class.
Okay. Well, try running that. Shows right. Okay, now try the ready to try to see what. This, uh, then maybe you can try using this on. I'm sure why this is. I never seen this before. So why don't you see where you know where your R is? Maybe go to search for R to get bypass.
And then the alpha.
Yeah, but the fact that you have also you actually have R like the basic. Uh, okay, try looking for. Yes, see R 4.5 times to this one. So try back run this one. Click on that. I'll go to file. Use go. Okay. What you do now is copy the ISO code, run it here, but this one you run code by pressing it. It's not a big, this is yeah, control. See that helps.
Okay.
So it's so beautiful.
Do I need to run library HH again?
Yes, everything. I think you don't have to install package because I think it's installed. Let's see. Okay, so it's oh okay. Good, it's loading the this is
No, it's okay. And then I didn't delete anything. I
Yeah,
just changed the flag.
delete. I think honestly, why don't you try doing this again? Delete these lines of code. Paste the one that I did across. Try rebooting it. Then. Good. So I see that there's a group that has made the R plot. I'm glad to see that that's good. You just change the names to what they are relevant to your data set. And get it worked out. So you should be seeing a plot like that for the box plot. The histogram, I would be interested to see what it looks like. I've not even looked at that one. So if you ran the let me see if there's is there a histogram here? Yeah, I will look. We will. Thank you. Yes. So I might scour the internet to give you an option of plotting histograms in part of the pattern, so it doesn't superimpose like this. This looks cool, but it's not very useful, is it? Right? Because everything kind of gets bunched up. Actually, is this telling you something? The fact that the histograms are so uh, superimposed this way, what does it tell you, anyone? What does it tell you, really? Not statistics, just using common sense. Yes. That's right. The diets don't seem, if there's any diet, that might stand out, which one is it? Can you tell from the picture? Are the colors helping you? Is there any diet, if there's any diet that hopes to be, I mean, okay, which a diet is good if most of the BMI change is what? Negative or positive? What's the goal of most diets? To lose weight. Yes, I know there are diets to get gain muscle and all that kind of thing. But in general, diets want to help you lose weight, which means a diet that is effective should have most of the BMI changes be negative or positive? Negative. I find that most of them are not doing that well. If there's any one that's a little bit more negative than others, which one is it? Atkins. How can you tell? Because you see, Atkins' color is, well, this red thing. So there are more red on this tin. That's the only thing. So see, based on just the picture alone, if there's any diet that's effective, it's probably Atkins, but the rest are indistinguishable. So it's very telling, this histogram. Yeah, I think I will go look for a simple code that you can do so you can plot the histograms separately so it doesn't get bunched up together like that. This is nice, but there's too much overlap. It's hard to look at things. All right, but this is correct. Okay, so maybe we'll discuss the first few questions. I'm not sure why these pictures have moved here. Um, okay. So what are the observational units? It's correct. It's the people. So you can check the answers that you have. I just want to discuss the first few word problems. The people are the observational units because you are, well, getting your variable data measured on them. So that's good. Identify the explanatory and the response. Explanatory is a diet, yes. It's categorical, there are 4 diets. And the response is the BMI change, important. Not BMI, BMI change. That's why you have negative BMI change. I mean, no one has a negative BMI. So BMI change can be negative, and that's quantitative. Good. What is the overarching research question? Obviously, I would just change this to which diet changed the most, or which diet resulted in the loss of BMI that was something like, I think that's what the key is. You're comparing 4 diets. You want to know which diet basically changes your BMI in a negative way, something like that, right? Then, does this study make use of random sampling, random assignment, both or neither? It's actually both. And how can we tell? Well, I did tell you a random sample of people were randomly assigned. So both. And what are the implications of your answer to with regards to scope of interest? You can tell me quite briefly. What does random sampling allow you to do? It allows you to generalize. What does random assignment turn the study into? An experiment which allows you to
Proof causation.
prove causation. If you find Atkins is associated with the greatest weight loss, I'm just going to say weight loss, BMI change. If you find that Atkins is associated with that, you can say Atkins caused that because this was an experiment. Right? Something like that. Define what mu Atkins is exactly. So mu Atkins is the long run mean. Okay, I would just make a small change. Mu Atkins is the long run mean. It's not, I'm glad the quantity is that it's not BMI, it's BMI change. That's very important. So it is the mean BMI change on the Atkins test. These are small things, but they are quite important. I want you to look at H naught. Is this the right notation to use? The idea is correct, but what should it say? How are null and alternative hypotheses always expressed in terms of?
Associations.
Well, you can use. Okay, so I did. Did I
This
say?
is an experiment, so
Right. So first of all, okay. This is a symbolic representation, which is fine. But is there something that's not 100% what you should have written here? The idea is correct. Anyone know what I'm getting at? What should this say? What should the null say? Yes. Mu A, mu Z, mu O, mu L. Why? Any null hypothesis never states it as in terms of sample size. Do you know why? Does anyone know why you do not write a null hypothesis using sample statistics here?
because your samples might differ just by nature of
Yeah, and also, do you need to hypothesize about sample? Have you seen that? That's right. So the logic is you don't know what parameter values are, so you hypothesize. That's right. So change every very good. Anyone know how to say this in lay people talk without using symbols? I did ask for that as well. What does the noun say? That there is
no association.
no association between diet and BMI change. Something like that. The alternative is there is one. I'm teaching you all aspects because sometimes people don't want to see symbols or they don't understand symbols, so you want to say it in a way that most people understand. You do not have any understanding of statistics. Very good. Use R to help with the following. I can see clearly that you have used T-apply well. Correct. Very good. Maybe if you want, you can put one sample code for this one. What code did you use to get this? I mean, it's not necessarily you have the code already, but you can show the class what code did you use to get this, because this is correct. Right? R spit out it's a T-apply thing. So you can put your T-apply code just underneath. Okay. I want to know, did any group perform a statistical test to see if there's evidence that and the histograms and box plots I've already talked about. Perform a formal statistical test to see if there's evidence. Did anyone try that one? Yes.
But I tried it.
Did your aunt? So there was something.
Yeah, I don't know. I think I did.
That's okay. So if you did, let me get it from your page. I'll just paste it here. So, let's move it down. Yeah, thank you. Okay, so, okay. Actually, doesn't the histogram look like the TikTok logo now? You know, the quaver that looks slightly off. I always think I'm having high blood pressure or something. I haven't seen double. Right? So anyway, here's something that would help you and me. This is not wrong, but next time when you paste things from R, why don't you paste the text? uh, uh, I know pictures you do a grab, because this one I have to copy a picture. It's not wrong, but it is helpful if it's a tinsel font. Let me see the picture copies. I'm sure it does. Let me. Yes, it does. Thank you. Yes. So you do the Brown Forsyth test. Now, what was it? P-value pretty big. So is there any evidence that the SDs are not the same in the population? No. So in other words, can we proceed with our analysis? Yes. All full steam ahead. So we can. Okay. Describe what the graphs and statistics reveal. We've talked about it. They reveal what? That just anecdotally, there doesn't really seem to be much difference between diets. In fact, I don't even know whether you have heard of any of the diets other than Atkins. Really. You know, Zone. I did it until I saw this data set. All right. But anyway, calculate as food. Maybe I will leave this for next week because this is a little bit technical. I will talk about this though. What do you think the VCs sound like? Anyone want to start us off? It has to be an yes.
10 observations in each group, right?
Okay, so it's not 10, but that was good. Yes.
20.
Okay, why? Because aren't we in quantitative world now? Right. So we need at least 20 people. Let's be not 2 people. We need at least 20 people on each diet, which we did have, I believe. If you check the tiers, right? I think we did. And then, what do you think the next one should sound like?
Data is not too skewed.
Data not too skewed. How can we tell that one? And we see this by, well, a couple of ways. You can look at the histogram, which doesn't look very skewed, actually. They are all bunched up together. And you can also look at the box plot. Remember, a skewed box plot has a very distorted median, is very much, yes, you can look at skewness in 2 ways. So that one. What do you think the third, okay, the independence one, I think we always like this. There is a third thing that I'm going to introduce. Anyone have any guesses what that sounds like? This is new. Anyone want to try? Okay, yes.
Oh, don't your residuals, this is more for, this may or may not work, but
Yeah, I know what you
don't
mean.
you have to have like no patterns in your residuals?
Yes, that's coming up.
Oh, it's later.
Right. You see, that's why there's no end to VCs actually. Because if you say there's just 2 or 3, actually there's a whole bunch. We are just going with the most important ones. The third thing that I want to introduce is you can say this. Variances of SDs not too different. And do we have a formal test for this? What's it called? Brown Forsyth. Which was, did it give the green light? Yes, the Brown Forsyth said go ahead. So this, we have a formal statistical test. BF test says okay. Yes. Yes, you should check the residual plot that's coming up. But that is like, in terms of building on fire, it is
5 or 6. I
yeah,
imagine.
it's like priority 5. That's right. Yes. Good. All right. I think we've done well. So I'll have a good weekend. I'll see you all next week. We'll pick this up next week. Thank you.